The next type of reaction is an acid-base reaction, another reaction that's covered in Chapter 8, and when we'll talk a little bit about pH and just simple acid-base reactions in Chapter 8. And in Chem 32, you'll get into pH and buffers and all that stuff. But a nice, easy acid-base reaction that pretty much everyone is familiar with would be to take acetic acid. So I'm going to draw this a little bit suggestively here. Sometimes, they'll take that whole molecule and they'll write it as a molecular formula, and you'll often see the acidic hydrogen out front. So what I mean by that is sometimes you might see this. They'll turn it into a molecular formula, so C2H3O2, and then they'll do this, and they'll stick the acidic hydrogen out front. The acidic hydrogen is here, and it's the acidic hydrogen for a reason. Not really a reason we care about in Chem 31, but I just wanted to let you know I drew it this way because the actual structure for acetic acid is this. So CH3, C double bond O, and then OH. And there's that acidic hydrogen. So I like to draw my acids out a little bit suggestively, especially when they're organic, so that I can see, number one, why that's the acidic hydrogen. Remember, with your polar covalent bonds, and you can draw, you can draw a resonance form for acetic acid. But anyways, moving on. So this will be aqueous, right? So we only worry about acid-base chemistry, or pH anyways, when we're talking about aqueous solutions. And I'm going to add a base to this. So sodium hydroxide aqueous. So what this looks like, and because acetic acid is weak, we'll use this arrow, right? We don't get 100% dissociation of the acetic acid in the water, so we don't 100% use all of that molecule to protonate 100% all of the base. But what do you get on the other side is the conjugate base. What does that mean? It means you take your acid and you take a hydrogen away, and it'll probably coordinate. So I'll have a negative charge on the oxygen, a positive charge on the sodium. And by the way, the sodium doesn't change from left to right. It looks like this over here too, right? So that's what we call a spectator ion. You can go ahead and feel free to leave it out of the reaction equation. It's just hanging out and watching. We call them spectator ions. And what do you get? Well, if hydroxide takes a hydrogen off of acetic acid, then you get some water, right? OH minus plus an H is H2O. So this is a type of acid-base reaction. There's all different types of acid-base reactions. We'll cover them in more detail in Chapter 8, but this is a reaction type, and so I just wanted to make sure that you guys were aware while we were going through reaction types. Combustion reactions. So again, we're going to take a hydrocarbon. Let's take a nice, easy, simple one. Methane. It's the smallest hydrocarbon we have in the gas phase. And we're going to burn it in the presence of oxygen gas. Burning the hydrocarbon in the presence of oxygen gas is a combustion reaction. And what you get is CO2 and water. So depending on the amount of heat that's being used, you can either have that water in the liquid phase or you can have it in the gas phase. Typically we'll write this in the gas phase. To balance this off, we'll just do this. So that's a type of combustion reaction. What are you noticing? Well, we have a hydrocarbon and it's burning in the presence of oxygen gas. The oxygen gas is crucial. If it's not there, it's not a combustion reaction. And again, a precipitation reaction. This is where we're going to take, it's really easy to see when both of your reactants are soluble. So say sodium chloride, dissolve that in a glass of water, right? Take some silver nitrate. All nitrates are soluble in water at room temperature. And what are we going to get? Well, on the other side, so here's another situation where we're doing a double displacement reaction. So we're going to swap dance partners here. Sodium and nitrate are going to hang out on this side. All nitrates are soluble, so aqueous, but silver chloride is not. That is a solid. And if you were to look up on a table of electronegativities, and you were to plot the average electronegativity relative to the difference in electronegativity, you might be surprised to find out that silver chloride is more covalent than it is ionic. And that might come as a surprise because you're saying, wait a second, silver is a metal and chloride's a non-metal. And you know what? No one cares. We're actually trying to figure out the lattice energy, right? And the nice, crude, quick and dirty way is to take our bond type triangle and do a comparison with, again, this sort of like non-measurable, ratio. We're comparing electronegativities. And it's arbitrary in the first place, but if you were to do a comparison for silver chloride like that, you might be surprised at how covalent or how more covalent it actually is. Later in the semester, when we go into lattice energies, we could calculate the lattice energy for silver chloride, and you can actually see why it's pretty darn hard to dissolve silver chloride in water. It's a solid. In fact, when you want to measure the amount of chloride anion in an aqueous solution, very often silver nitrate is used. And if there is the chloride ion present and silver combines with it, then you get a precipitate. And as long as you know everybody else that's in the reaction pot, and you know, like, for example, if you're going to be doing this reaction, the only other possible product that you could make is sodium nitrate, which is soluble. If you do get a precipitate, because by the way, sodium chloride is a clear, colorless liquid, right? It's an aqueous solution, and so is silver nitrate. It looks like you're pouring 2 test tubes of water together. It's really what it looks like. But then all of a sudden, poof, this like cumulonimbus cloud appears. That's the silver chloride. So that tells you, well, I know that the sodium nitrate's soluble. I know that silver chloride is the only other thing I could make, and I see a precipitate. So I must have had chloride. So it's one of those qualitative experiments that you can do. So we're going to move on into some stoichiometry. This is where we're going to have some calculations that we're going to do. So really what we're talking about when we talk about stoichiometry, literally it means the measure of the elements. And so when you're looking at sort of a baking recipe, and, it's 2 cups of flour to 1 cup of sugar, or, who knows what, you need half a cup of water and, a teaspoon of baking soda, or whatever it is, whatever you're combining, all of those ratios, right? It's sort of telling you how the reactants and the products relate to one another quantitatively. So the difference between qualitative and quantitative is coming back to us from, what was it, chapter E, right? So qualitative is like, is this blue? Quantitative is, how blue is this? There's a difference. See, if you can measure something, you're quantifying it. And so when we're working out these stoichiometric problems and these calculations, you absolutely must begin with a balanced chemical equation. So if you are not feeling particularly solid in that department, I would brush up on those skills before going into stoichiometry problems. Once you've mastered balancing chemical equations, you can move into stoichiometry. And why is that? Because you absolutely need a balanced mole ratio of all your reacting species and all of your product species. Otherwise, you can't do these calculations, because you're going to see now how we're going to use those numbers. So for the first example, we're being asked to calculate the mass of oxygen released when enough mercury 2 oxide decomposes to yield 0.125 moles of liquid mercury. When you read these problems, you have to zero in on the precision of their language. The word enough is a big deal in this problem. They want you to calculate the mass of the oxygen released. Released is a big word. What do you think it means? It means oxygen is a product. And then it says when enough mercury 2 oxide decomposes. We're doing a decomposition reaction, right? And so if we're doing a decomposition reaction, we need to take mercury 2 oxide on the reactant side And the word enough means they're not going to tell you how much was used. Simply enough is enough, right? You're going to be making oxygen gas and liquid mercury. And they're telling you that you're going to get 0.125 moles of liquid mercury. So you really need a balanced chemical equation to figure out what the mole ratios are. How does all of this work? So let's first draw out mercury 2 oxide. So HgO, right? And this will be a solid. And this is going to decompose. So off it goes. Those are your reactants. Now on the other side, what are you going to get? Well, you're getting liquid mercury. And you're going to get oxygen gas. Now, no one's expecting you to know that mercury 2 oxide is a solid. Typically, in one of these questions, if it's necessary that you know what the physical state is, then it'll be said solid mercury 2 oxide. There's no harm in telling somebody that that's a solid, right? For now, I'm just going to say, okay, this mercury 2 oxide is going to be a solid here. But I have to balance this reaction equation because it's not balanced right now. Do you see how on the product side, I have 2 moles of oxygen atoms in molecular oxygen? And on the reactant side, I've got 1. So I'm going to put a 2 in front of mercury 2 oxide. And I'm going to have to put a 2 in front of mercury. Wow. Did you see that? This is another one of those random weird little shapes that the stupid iPad makes. Okay, so we have a balanced equation, right? And now we can say, well, if I want to know the mass of that, right, when enough mercury 2 oxide decomposes to yield 0.125 moles of liquid mercury, what are they actually asking me? Well, the word enough means you don't have any numbers to use. So you know what? You have to go with what you're told. And right now I'm told that 0.125 moles of liquid mercury, right, are produced when enough of the mercury 2 oxide decomposes. So I want to know what the mass of the oxygen is. And there's no way to compare that to the reactant when I don't know how many moles of the mercury 2 oxide or the mass. I know nothing. I just know that enough of it decomposed. But I do know the mole ratio between the two products, don't I? I do know that for every 2 moles of liquid mercury produced, only 1 mole of oxygen gas is produced. So I can figure out the number of moles of oxygen gas by knowing how many moles of liquid mercury are produced by this reaction and by having the balanced chemical equation. What am I talking about? All right, let me show you. So we're going to take the moles of liquid mercury that are actually produced, and I'm going to say that for every 1 mole of the reaction that occurs, 2 moles of the mercury are produced. And when 2 moles of liquid mercury are produced, 1 mole of oxygen are produced. So now I actually have an amount of oxygen gas that's produced when enough mercury 2 oxide yields 0.125 moles of liquid mercury. They want to know the mass, not the number of moles. And I know that 1 mole of molecular oxygen is going to have a mass. So if you look on your periodic table, and you know, we can feel free to round this up, I guess. Oh, it's 16 times 2, so it's O2, right? So this is 32. We'll just call it 32.00, right? It's like 15.9994, really, times 2. We'll just round it up for this calculation anyways. So I've got 0.125 moles of liquid mercury, and my moles of mercury are going to cancel out. I know that my mole ratio, So here's my mole ratio of products. It's how I know how much oxygen was made. I don't even need to know how much of that stuff decomposed on the reactant side. I know how many moles of just one of my products was obtained. And I know the mole ratio of everybody in the pot. So I know that only 1 mole of oxygen gas is produced when 2 moles of mercury are produced. But I also know that only 0.125 moles of mercury was produced. See what I'm saying? So you can take that mole ratio, multiply it by the actual amount of mercury that you made, and you can figure out how much oxygen you made. And my moles of oxygen are going to cancel. So what I end up with is about 2 moles. Hang on, let me grab a calculator to make sure I'm not lying to you, because Amy and math without a calculator sometimes, if it's arithmetic, is not pretty. All right. I think it's 2. Watch it not be 2. So 0.125 times 32 divided by 2. Yeah, it's 2. Okay. All right. That's refreshing to know. So 2. And check it out. The sig figs on this. So, and it's 2 grams of oxygen. Right, you guys? So it's 2 grams of oxygen. I know that it's grams because that's the unit I'm left with. There you are. I know it has 3 sig figs, right? Because I've got 3 sig figs in. So here's 3 sig figs here. 3 sig figs here. All right. So the first thing we did was we wrote out a balanced chemical equation. We needed that balanced chemical equation, so this right here allowed us to do that. Without the balanced chemical equation, you wouldn't know that it was a 2-to-1 mole ratio, and then, you'd be sitting there going, so why are you talking about liquid mercury when you're asking me about oxygen? Well, that's why, because you don't know how much stuff you started with. You just know that it decomposed and gave you a specific number of moles of one thing, and they're asking you about the other thing. You can compare anything you want. You could have compared the oxygen to the mercury 2 oxide. If they told you 10 grams of that stuff decomposed, you can figure out the mass of the oxygen. You could have figured out, the mass of the mercury. Whatever you like. As long as you start with a balanced chemical equation, you're golden. You can go anywhere from there. So, let's do another one.